Okay, welcome back. Now this is part 2, but by the way, we just come to the point of, the linearization and other stuff. So I promised that this recitation was about, so if you remember, this was about linearization, gradient and direction derivative. But I'm sorry, I mean, the first part is like, we just revisit or we just have discussed further questions about basically higher differentiation. But now we come to the main point. Okay, I'm sorry if for any convenience, I'm sorry. So let's see. Now we are going to discuss actually linearization. And maybe we should first remember the meaning of linearization, right? So if you remember, just okay, the solution. So we just recall, okay, in one variable case, right? One variable case. If we have a function which is a little bit complicated, right? For instance, something like this, and around some point A, right? Around some point, by using its tangent line, right? So we can compute any value near the point A. For instance, over here, a point X here, but instead of computing that value, we compute this one. Okay? Therefore, we compute actually this. So Lx is actually the tangent line. Okay? So be careful. So we have the point A, FA. Okay? And then actually, if you really compute the slope, remember, so maybe we need to do this, but let's recall, right? This is the slope. But when exists, slope can be given by the derivative of f, right? And so actually this tells you, right? This gives you something like this. So Lx is just f prime a x minus a plus fa. This is actually the equation of tangent line. But by using this tangent line, you see, instead of computing this exact value, right, we can approximate it, right? So this is actually gives you, so we just want to approximate f, or approximation, if you like. So approximation is better. Approximation of f for x, any x near a. So this concept is given like this. So it is approximately given by this linear equation. Okay? And this is called actually, so Lx is called a linearization of f, at center, if you like, x equals a. Okay, so by using this idea, actually we can generalize this idea, if you like, right? So we can generalize in higher dimensions. Okay, so is it possible to go this way? Okay, anyway, so it can be generalized to higher dimensions. Okay, but now of course instead of tangent line, instead of this concept, of course we use the tangent plane. Of course, we replace with this concept with the higher dimensional counterpart, which is the tangent plane. We use the tangent plane. P at instead of now we have two components at the point AB to give a linearization of f. So what is the picture if you remember? So now so we have a surface like this, if you like. Now at this point, so let me sketch like this. So this is exactly the point AB, and now near AB, for instance over here, this is some other point xy, right? And now we have the tangent plane like this. Okay, so this is the tangent plane, if you like. So this is the P, this is the tangent plane. So this point is exactly A, B, and f of AB, right? But now any point near this AB, right, we compute, as we did in the previous case, the tangent line case, a very close point, and this point is given by xy lxy, right? And this is exactly, right, the tangent plane. Therefore, what we have is the following: the linearization of f, right, near AB is just lxy equals f1 AB x minus a plus f2 AB y minus b and plus f AB, right? But if you look at carefully, so this is just, the tangent plane, right? Then we write for the approximation, right? We write something like this. Okay, so we try to approximate the value of f at some point xy by using certain tangent plane, if you like, at some point AB. Okay, so we want to write down a linearization centered at the point AB. Okay, fine. So this is the idea. So this is exactly, if you remember, the equation of the tangent plane. And look at the similarities, right? Look at the similarities over here. Now we have two variables here, xy, just forget y and the component b, right? Then you end up with exactly the same equation over here, right? Fine, so this is the idea. Now in our case, we should define some function. We define our function to be square root x and e to the y. Okay, very simple one. And we want to approximate the number. What was the number? Number was something like this, right? Exponential 0, this. And if you look at carefully, this is exactly the value. I mean, this is just value of f evaluated at the point 0.99 and 0.02. Okay, and then we want to approximate, and we use the linearization of f at, so we pick some specific point, right? So at which we can at least compute the value of f, and of course we can construct the tangent plane. And the point we are looking for, the logical choice is, of course, 0, 1, 0, because 1 is close enough to 0.99 and 0 is close enough to 0.02. Okay, therefore we choose our center, if you like. This is the point AB, actually, in the definition of LX, linearization. And now we are going to construct this. Okay, just observe that f sub x is something like this, right? So it's easy, no problem. And f sub y is exactly the same thing, right? And so when we compute, so f sub x 1 0, right? This is 1 over 2, and f sub y 1 0, this is 1. And of course f of 1 is, f of 1 0 is 1. Okay, and then so f of xy can be approximated by Lxy, and Lxy itself is, just use the definition above, which is just 1 over 2 x minus 1 plus, okay, 1 times y minus 0 and plus 1. Okay, therefore I mean, that's all. This is how to approximate f by using such a linear function. So this is the idea. So you have a function which is complicated, but we are going to approach values by using suitable linear function. Okay, so this is a linear function. If you look at carefully, L of x is just a linear. And so f just computes 0.99 and 0.02 is approximately, is just, okay, 1 over 2 minus 0.01 plus 0.02 plus 1. So this is just 1.015. Okay, so this is approximately this number. Okay, so if you like, therefore the result is, okay, you got this, right? So this is the idea. This is approximately, okay, that's all. Okay, okay, fine. So next one. Okay, now next one is about gradients and directional derivatives. Okay, so let's see. So part A, we are going to compute the gradient of f at the point, okay, p0. So we should remember, so what was the gradient of f at the point p0? This is just a vector, right? Given like this. Okay, something like this. And we are going to evaluate this thing at p0. Okay, but now this is not that much hard because f is given. Differentiate this thing with respect to x. Now we have 1 over y. Differentiate with respect to y. Okay, something like this. And differentiate with respect to z, which is minus 1. And evaluate it at p0. And this gives you a vector like, okay, what is p0? Okay, 1, minus 3, and minus 1. That's all. This is the gradient vector. Okay? So part B. So the question is there a unit vector u such that, okay, the direction derivative attains such a number? Okay, so if you remember, we have a limit definition of directional derivative, right? Of course. But actually, if you have a nice function, which means that it is differentiable, and then directional derivative can be expressed in terms of the unit vector u and with the dot product with the gradient vector. Okay, so it can be expressed in terms of a dot product of two things actually. Okay, so since f is differentiable, at p0, actually it can be, so check this. Okay, check y. Actually, you should check partial derivatives and also continuity of those things. Okay, check y. Okay, and then for any unit vector, u. Okay, so what we have, so this directional derivative at p0, so it basically gives you the rate of change in that direction, okay, manifested by the vector u. Okay, very nice. And the gradient f evaluated at p0. Okay, if you remember, this sort of interpretation has some geometric meaning. Also recall that the maximum rate of change, right, is in the direction of gradient, right, with magnitude, of course, the magnitude or the norm of the gradient vector. And the minimum, this can be easily seen, just check the lecture notes if you like, by just looking at the definition of a dot product in terms of, you know, the norms and cosine theta. So minimum rate of change is in the direction of minus, and with the magnitude minus this thing. Okay, but now if you compute that, but here if you really compute gradient, or if you like, okay, so here we have something like this, minus this du f p0 and df p0. But if you compute, just look at the norm of this vector. This is just, you know, square root 11, right? And this is already less than 5. Therefore, there cannot be any vector so that the directional derivative attains the value 5, okay, at the point p0. So there exists no vector u such that du, okay, f p0 is 5, okay, because the maximum value is square root 11. Okay, fine, but there could be a vector, but part C, there could be a vector. So we have one more thing. The next question is about, is there a unit vector with this rate of change is 3? But now it is possible, right? Because 3 is in this range, minus square root 11 and the square root 11 range, right? And I mean, the 3 is in this range. So it says that it is possible to find u, a vector with, of course, this is a unit vector, right, such that the UFP0 is 3. Okay, but of course this is actually boils down to study certain equations, right? So be careful. That means, so we have 3 equals to, by using this dot product definition, so you have u1, u2, u3. This is actually how we represent the vector u, if you like. Dot product 1 minus 3 minus 1. Okay, but of course this means that we have u1 minus u2 minus u3 should be 3, but also keep in mind that we have something like this, right? Because the unit vector, and therefore we are then actually, there is actually one possibilities. Just take, actually among those possibilities we have, I guess, okay, at least we have one possibility, which is this vector 0, minus 1 and 0. Okay, this satisfies the linear relation, and also its norm is 1. Okay, and we are done. So what about part D? Part D is a little bit weird because the part D says that, so let S be the set of all points where f increases fastest. Actually, we know that f increases fastest in the direction of gradient vector. Therefore, we know that, so recall that f increases fastest in the direction of its gradient vector, right? Therefore, the set S, so the set S, so the set S is given by, so let's write it down. So this is a set. This set consists of all possible points x, y, z in, okay, domain of f, if you like, okay, such that if you compute the gradient vector at that point p for any of those points, this should be parallel to the vector a. And the vector a is, okay, what was it? Okay, 2, 1, 2. Okay. Therefore, we really want to understand this set. Okay. But be careful, what is the meaning of this thing? i.e., gradient f evaluated at p is just some constant times a dot. Okay. And if you like, so direction is important. So just rescale a by taking k to be minus 1 over 2. You will understand the reason, because when you do this, then we have something like this. P is exactly the vector, okay, with this rescaling. So we have minus 1 over 2 and minus 1, right? But maybe I should write like this. Okay, this thing is equal to gradient f evaluated at p, but the gradient f we already computed, right? So what was it? This is something like this: 1 over y minus x over y squared and minus 1. Okay, therefore this gives you 1 over y should be minus 1, minus x over y squared is minus 1 over 2, and that's all. I mean, because minus 1 is equals minus 1, so no problem. So therefore this is true whenever y is minus 1, x equals 1 over 2. What about z? Z is free. Z is free. Let's say z is equal to t, and the t in R. Okay, what does it mean? So that means the set S consists of possible points x, y, z in domain of F, if you like, such that, or maybe I should write like this. This is 1 over 2 minus 1 and t. Okay, such that t is in R. Okay, so this is the set S. But what is this? Just look at carefully. This is just, so let me sketch it. Okay, so this is x, y, and z. This is exactly the point we are looking for. Right, this is the point x 1 over 2, y minus 1. But since z is free, that means that you have a line. Okay, this is exactly the set. So set S, which defines a line, L with the equation. Let's see, you should remember how to give the equation of a line, and this is exactly something like this. So let me write it down in a vector notation. Okay, this will be the case. Okay, t times 0, 0, 1. Okay, this is exactly the equation of this line. Okay, with the direction vector, if you like, this 0, 0, 1. This is the direction vector. This is the parametric equation in vector form, or I don't remember its name, something like this. Okay, so this is the equation. Okay, that's all. This is the set S. Oh, so the question is describe the set S. Okay, so the question is describe the set S. Okay, sorry. Okay, fine. So that's all. Okay. So we are done. Next one. Now next one is about level surfaces. Okay. Now we are going to write down the equation of a tangent plane to the level surface of a function. Be careful. We discussed this. I guess in the previous lecture we discussed this, right? So just recall our solution. If we just let t equals f of x, y, z, and f of x, y, z is exactly given like this, just consider t as a time, right? So that was the motivation, if you remember our previous lecture. Just consider t as a time, and then when t is fixed, when t is a fixed number, you just take a kind of an instantaneous picture at that time. Okay, therefore so we have this. So recall that. So this thing, so over here t can be viewed as a time parameter. Okay, so for each fixed t equals t0, okay, so t0 equals fxyz is a kind of a gives an instantaneous picture, and it turns out to be a surface. Okay, sorry, turns out to be a surface. Okay, so the picture is, if you like, but in our case, so at p equals 1, 2, 3, so we have the level surface is actually given by xy divided by z square equals to, just compute exactly the value of f at that point. So this is exactly the value when you substitute 1, 2, 3 inside the definition of f, right? That's all. So this is the level surface. So if you like the picture, so when, if you like, t equals 2/9, so we have a surface. So somehow we have a surface like this. Okay, so this is exactly certain tangent plane over here. For instance, like this. At this point, for instance, so we have xyz planes. So this is exactly xy divided by z square equals 2/9, this surface, right? This is our surface. And then we have a tangent plane here. The best part is the important recall. This is the first recall. And the second recall is the gradient vector is exactly normal to that surface at the point P. So this is exactly the point 1, 2, 3. Okay. And then, so this is exactly the normal. Therefore, this is really parallel to that one. Okay. So the recall is Fp is normal to the level surface. Of F passing through the point P. Okay, so that's all. So just therefore we just compute gradient of F at the point P. So let's compute. Therefore I'm just going to directly compute. Differentiate with respect to x, we have this. Differentiate with respect to y, we have that one. And differentiate with respect to z, minus 2xy divided by z cube. And evaluate it at the point 1, 2, 3. Okay, and then if you compute, we have 2/9, 1/9, and minus 4/27. Okay, and now because of the recall 2, so we have a recall 2, and since this gradient vector is parallel to normal vector and the direction is important, just take, I mean the scaling is not important, the direction is important, okay? So just take the normal vector of this tangent plane to be 6, 3, and -4. Okay? I mean, what I have done, I just multiply this vector with some constant, right? The constant is actually 27. So I get rid of the denominator, but we have some multiplication by 3. Okay, so that's all. Then you know the normal vector, you know a point on that. Maybe this thing is a certain plane, but it's a curly. Okay, so it's a point P and the plane. So the equation, and so an equation of the tangent plane P at 1, 2, 3, if you like, is given by, I don't know, if you like, we can directly write it down. This is just 6x minus 1 plus 3y minus 2 and minus 4 z minus 3 equals 0. Okay? Or if you like, if you just rearrange the term, certain algebraic manipulations gives you, I guess, something like this. Okay, that's all. Okay, so this is the equation of the tangent plane. Okay, that's all. Okay, the next one. Now, next one is about implicit, I guess. What was the topic? Implicit? Okay, implicit differentiation or something like this. And of course, we did this before. If you remember our previous course, Math 119, we did this. And actually, in this course, if you remember, you were not allowed to use certain formula, right? But now we are going to prove it. And now, up to now, you can really use actually the advantage of two-dimensional point of view, so that you can really use the formula that you have you weren't supposed to use in the previous lecture. Okay, I mean the lecture of the previous semester, if you like, the previous course. And then just observe that to do this trick, you need to define a certain function of several variables. Over here we have a function of 2 variables which is defined like this. Oops. Okay, and of course we have the equation with the equation f(x,y) is 0. Okay, so we have this function and we have an equation. So the question is, first you should check that whether the variable y can be expressed in terms of x or not. Okay, and then you should, of course, for the exact theory, you should go and check the lecture notes. But the theorem actually says that it is enough to check first, if you differentiate f with respect to second variable and evaluate it at the point, should be non-zero. Okay, and the second one, actually all partial derivatives exist and are continues at that point. Okay, but now let's clearly observe that. Okay, this part is more or less clear, right? Because if you look at all partial derivatives, right? So you have a sine, ln, so at that point everything actually goes smoothly, no problem. But the crucial part is, let's compute this thing, right? So if you compute it, so let me write it directly, if you like. Just differentiate with respect to y. Okay, ln x. Okay, yx. Computed at 1, 0. Okay, we have 1. What is it? Is this? So we have 1 here. So this second part is 0. So this is 2. So this is obviously not 0. Therefore, just so given equation, given implicit equation can be solved for y as a function of x. Okay, we just say that y is just function of x. Okay, function of x with, of course, the value should be f1 should be 0. Okay, so with this observation in hand, just to find dy dx, just observe that, so we have a dependence relation. So f itself is now depends on x and y, and the y itself depends on x. Okay, so taking derivatives of both sides of what? This equation, right, with respect to x, gives the following, right? From chain rule, so we should first differentiate f with respect to the first variable, plus differentiate f with respect to second variable, plus differentiate second variable with respect to first variable, with respect to x. Okay, and this is 0. So we end up with the formula, right? A certain formula. So which was not allowed to be used in Math 119, but now by using higher order interpretations and functions of several variables, now we end up with this formula. You see, there is a theory behind this, so we should be careful. Then we should evaluate that thing. But now this is easy. This is just y cosine xy plus y over x plus y times something like this, and divided by, I guess I learned how to do the trick, so let me try once more. Okay, copy and paste. Okay, it's very unnecessary move, but anyway. Okay. Okay, so I feel happy. I'm sorry. Okay, fine. So if you compute, so the denominator was 2, and if you compute the numerator, it is 0. So it's a 0. Okay. Okay, fine. So this is implicit differentiation, and I guess that's all. Okay. So it's good place to stop, I guess. Maybe I should stop. Okay. Then thanks. See you next time. Okay. See you next week probably. And next time we are going to discuss chapter 13, I guess, right? Okay, thanks. See you next time.